Matrix equations are widely used in different fields of science and engineering, as equations involving multiple variables arise at different stages of computation and analysis. So, these equations are usually of the form of A x is equal to b, where x is a vector comprising all the solution variables and A is a rectangular or a square matrix, where the rows represent each equation in the system of equations and columns are multiplied with the solution variables. Now, A x is equal to b, this matrix equation can be solved using two broad class of methods. One is a direct solver, another is iterative solvers, and all these two methods has their own pros and cons. Direct solvers are usually used for small system of equations, where iterative methods can be used for a large system of equations. However, they have their convergence issues, and there lies a plethora of techniques involving both direct solvers and iterative methods, which has been developed over not only centuries, over millenniums. As the first documented method comes from Chinese mathematicians by almost 2000 years back, which is later formalized as Gauss elimination method. And there are recent developments like generalized minimum residual algorithm, biconjugate stabilized method, and their variants for parallel and vector processors. So, in this course we will try to discuss over a number of methods, and interestingly the ancient methods like Gauss elimination methods has not been obsolete yet. In a sense, they are still utilized by several applications and as well as by several computer programs. And one important point in matrix solvers is that finally a large matrix cannot be solved by individuals in paper and pencil, it has to be taken to a computer program. So, we have to look into applicability of the matrix solvers in terms of implementation in computer programs. Matrix solvers are used in a number of fields like computational mechanics, where a typical finite element solution gives rise to a stiffness matrix, computer graphics, multibody dynamics, topology or surface rendering or CAD modeling, computational fluid dynamics. It depends heavily on solving pressure Poisson equations, which again are translated into matrix equations, network circuit theory, quantum mechanics. A branch of quantum mechanics is actually called matrix mechanics due to a heavy dependence on matrix solvers. Also in economics, Leontief input output model has matrix solvers, and in many other fields. And in this course we will try to see few basic aspects of matrix solvers, which will start off representing the physical systems as the matrix equations, and then looking into properties and structures of the matrices, then looking at doing some basic linear algebra and finding out the solvability of the matrix equations, whether the equation has unique or no solution and how to handle these cases. Then looking into direct solution methods and their restrictions on their applicabilities, and also looking into iterative solution methods and their convergence, and how we can improve the convergence using some modern techniques like preconditioners or multigrid methods. And of course, we will see how these methods can be implemented in different computer programs or codes. Thank you.